Hi again everyone. We're going to try working with a different example this time. Still from the Kinetics booklet, but this is task 5 question 2. So in this example we're told that the rate is equal to K multiplied by the concentration of J squared. So this example is different because instead of, like in question 1, both substances in the rate equation were first order, this example we have only one substance in the rate equation, which is J, and J is second order. So the rate is proportional to the concentration of J squared, and that's important, and you'll see why as we work through some of these examples. So let's write down what the question and the data tells us. We're told about the concentration of J, the concentration of K, and we're told the rate. So the example that we're given, the concentration of J is 0.5, concentration of K is 0.2, and the rate is 0.36, and that's the data that I'm going to work with to compare everything else to. So in the first question we're told that the concentration of K is 0.100 and the rate is 0.360, and we're trying to find the concentration of J. So we can see immediately that the concentration of K has been divided by 2, but K is not in the rate equation. We're not talking about this K, that's the rate constant. We're talking about the concentration of this substance K, whatever it is. It's not in the rate equation, which means it will not affect the rate at all. So although it's decreased by a factor of 2, because it's not in the rate equation, it cannot affect the rate. So we see that the rate has actually stayed the same. Nothing to do with K. So the rate stayed the same, so the concentration of J must also have stayed the same. J is the only thing that affects the rate, and the rate is unchanged. Okay, so next example. Again, we're trying to find the concentration of J. We're told the concentration of K is 0.2 and the rate is 1.440. So the concentration of K hasn't changed, but that doesn't make a difference because it's not in the rate equation and it won't affect the rate. So that change in the rate is just due to how the concentration of J has changed. So how has the rate actually changed? Well, 1.440 divided by 0.360 is 4. So the rate has increased by a factor of 4. So your instinct at this point might be to say, oh, well, J must have been multiplied by 4. But J is second order, which means that the rate is proportional to the concentration of J squared. So the question we need to be asking ourselves is, what effect on the concentration of J squared will give 4? Or what is the square root of 4? So the square root of 4 is 2, so the concentration of J must have increased by a factor of 2, so it must have doubled, and that gives 1.000. Just run through that again. So the concentration of J has doubled, a factor of 2, and 2 to the power 2 is 4, so the rate increases by a factor of 4. That's how you work with second order reactants in a rate equation. So the next one that I'll run through, and then I'll leave you to do the last one on your own. We're told that the concentration of K is 0.2, the rate is 0.180. I'm trying to find the concentration of J. Again, the concentration of K doesn't really make any difference because it's not in the rate equation. So how has the rate changed? Well, it's gone from 0.36 to 0.18, just in case you are wondering what that factor is. it's 0.5. So the rate is halved divided by 2 or times 0.5, however you want to think about it. Excuse me. So I'm going to prefer to think about it as being multiplied by 0.5. So how has J changed? Well, the question we need to ask ourselves is, what factor raised to the power 2 gives 0.5? Or, what is the square root of 0.5? And the square root of 0.5 is 0.707. So this factor here must be multiplied by 0.707. Can't quite see that one. So 0.5 times 0.707 gives 0.354. And that's how the concentration of J has changed to give the change in that rate. I'm going to let you try and do the last example in that question yourself, because that's an introduction on how to use the data to work with second order reactants. Okay, good luck.